Okay, team, let's go. 3 more lectures. A lot is going to happen. A lot of things are going to happen. These things will be on the final exam. No. But you'll need this for the 10th assignment, which is not yet declassified, and that you have to hand that in. You don't have to, but it will count. So there's a little game where you're allowed to drop one of the scores. The lowest one gets dropped through some MATLAB script of mine, but you can't drop the last one. Because, come on, what's wrong with you? This is not a soft option class. You can't drop the last one because it involves everything you've learned. And there was a point to this course. It's to learn about matrices. Maybe to love them. All right. Okay, let's see. So I have one assignment here that does not have a name on it. So you can, if you want this back, come look for it. This is assignment 7. Pick that up. I'm going to give you solutions to Pitfall, which you just hand in on Tuesday. I'll hand them around so you have them. Artisanal, locally crafted solutions. And what else? Right, so exam on Tuesday. Office hours are going to be shifted around a little bit on Monday, but look them up online or the tweets. I've tweeted about it, so it's in the website. Where is it? Where is it's in here, tweetage, right? All right, well, I'll put them up. They're not up yet. I'll put them up. What else? I'm trying to think of other things we need to talk about. Oh. So, the third challenge level, then there are two last lectures. There's a Thursday lecture and a Tuesday lecture, and our exam is on that following Monday. I think it's May 5th. Right? The final boss level. All right. Then it's all over, people. Yes? There will be a practice exam, which is what I think of as a study guide. Okay? Yeah. There will be a practice exam. There is a practice exam online now for challenge level 3. Good. All right. Okay, so today we're going to do positive definite matrices. This is kind of an excursion like we did with determinants. We're finding out more things about these crazy matrix business things that we have. For some reason, this will be relevant, right? We're going to play around with this. What is this an equation of? A chicken? What's it look like? If we drew this, and you're right, close, a banana shape. Tell me once again why the Earth is banana shaped. So Buenavir, okay. There's a word we can say. X1, X2. This traces out an oval, all right, an ellipse. There you go. Yep. All right, so that will have something to do with matrices because it's better if we do it with matrices. Everything is better with matrices. And we'll see elimination has something to do with completing the square, right? That's something you do with quadratics a lot, right? Okay. When A is like a positive number, we're going to get to that. This thing called, I'm going to say Cholesky, but I'm probably wrong. Factorization. All right. And then maybe we'll get to SVD. Okay. All right. But many charming, charming results, lovely little results about matrices are coming. Okay. Crazy things. Lots of things get tied together. I think that's what I needed to say. Okay. Yes. I'll get rid of that. Off. And right. Okay. Okay, good. All right, so we got somewhere, we defined these PDMs, positive definite matrices. We found this connection between, this is for symmetric matrices, right? We found this connection, strange thing, between pivots and eigenvalues, and I know you were excited about this, all right? So, last time, we showed, well, first of all, we had a PDM, positive definite matrix, and this is we're going to have another definition for it today, but the idea is it's A equals AT transpose, and lambda I is greater than 0 for all I equals 1 to n. That's our definition. Semi-positive definite matrices, lambda I is greater than or equal to 0. We had these two things, and we showed crazy thing that the number of positive pivots equals the number of positive e-values. And then we had all of this, so we had the negative ones and the zeros. All these things are the same, equals number of negative and number of positive, number of 0. Boom, boom, boom. So that's what we found. That's a strange business. Okay. That's just a good thing to know about these matrices. Now we're going to sort of go and use them in different ways. Okay. So why are we doing this? I'll reveal a little bit. Why are we doing this? Okay. So now we're going to move on to sort of usages of PDMs. All of this is going to help in one crucial part of singular value decomposition. We'll get to that. That's later. But we're going to explore and profit from this area. Okay. So here's we'll see one example of where this appears. So this is a common matrix construction. I'm just going to tell you that. Things that look like this. X transpose A X. Same X. And we'll see where this plays a part. So it's X transpose, it's 1 by n. This is n by n, and this is n by 1. And this is where A equals A transpose. Where A equals A transpose, right? So it's all for symmetric matrices. That's generally what we're working with here, symmetric matrices. Square, and they have to be square symmetric matrices. I've got this right. So what is this thing? What's the output of this? If I do this multiplication, I get what? Just a number, right? So this is just a number. Right? So this is a number. Numbers num, letters let. That's how it works. Okay, all right. That's just the English majors encoding things in words. All right, so it's a number. So this is kind of an interesting construction. So we'll sort of see where this appears in a few places. And how does this connect to positive definite matrices? So I'm just going to tell you this is a useful thing that appears in the world. And we'll get to it. So let's imagine, crucial result was that, we know if A equals A transpose, and A is real, we know two things. We know that the lambdas are real, 1, and 2, that the eigenvectors all exist. There are n linearly independent eigenvectors, and they're orthogonal. A crazy result. A has n, and this is an n by n, linearly independent e-vectors which are orthogonal, which form an orthogonal basis, and you can make it orthonormal, an orthogonal basis for Rn. So that's kind of bananas. And so what we can say is, well, we can write x like this. We can say x is, what's the way I'm going to say this? X is, say, yeah. So we can do this. X is C1 times V1 plus C2 times V2 plus Cn times Vn. Right, we can do this. So these are e-vectors. Right, we can do this for every, these are e-vectors of A. We can do this for every x. Do this for every x. It's a basis in Rn. Right, the V's form a basis. They form a very nice basis. Not just a basis, an orthogonal basis. The orthogonal part is not totally relevant here, but they form a basis. So we can write any x as some linear superposition of them. Right? So if we go back to this little beast here, and we write x as this linear superposition, back to this strange thing that we're working on. So back to this new thing. x transpose A times x. So if we stick this in, we're going to write C1. Well, should I write in sums for you? All right, well, I can do that. Sum from I equals 1 to n, the sum of Ci times Vi. And I'll make them, let's make them unit vectors, because we're good, we're being good people. Unit vectors. Sorry about that. So these are going to be unit vectors. Unit vectors. Okay. So that's x, it's x transpose. So this beast. Then we've got A, and then we've got a sum, again, of this, and I'll make it J. It's important to distinguish the indices. And because bad things can happen, this is going to be V hat. This is a V hat here. Put a little hat on it. Right. Okay, we can write x, any x right? This is any x. We can do this. So these V's are eigenvectors, so we use this because we love eigenvectors. We get some superpowers, things are simple. So we're going to have, on the left, this is going to stay the same. I'll just write it here. Sum I equals 1 to n, Ci, Vi. This is so great. And what happens to every A times Vj? What do we do with that? We just replace it with lambda j Vj, right? So this is going to be A times Vj hat equals lambda j Vj hat. Lots of triumphant things are going to happen very easily for us because we've been good and the monks have told us well. So we're going to have sum j equals 1 to n. Very important to have different indices. Cj, and now, sorry, I keep doing the wrong thing, and that's lambda j Vj hat. So next step, all of this blob, we can pull the sums out. So we're going to have these two sums, sum from I equals 1 to n, the sum from j equals 1 to n, and then we have these constant terms, Ci, Cj, we've got a lambda j, and then we've got where the real work is happening, V, this is a I, V hat, this character here goes here, and then a Vj. Got it? Yeah. It's an orthogonal basis, so what's this little blob? What happens to this thing? It's like I hat, J hat, K hat. These guys are all at right angles to each other. So they're all 0. So this is equal to 0 if I does not equal J. And equal to 1 if I equals J. So in math, I don't know if any of you have seen this, there's a thing called the Kronecker delta function. And that's exactly what this is. And this is actually called delta ij. Just really is annoying. We keep naming them after people, but I mean, who cares about the person, right? If octopuses did this, it'd all be called Scroobius Theorem, and I don't know what they call each other. Actually, they're not very social. They eat each other, so that's a problem. Hence, we will survive for a while. Delta ij is the Kronecker delta function. There's a continuous version, the Dirac delta function. Dirac was a very smart, obnoxious Englishman. Okay, who was smarter than everyone? What did he say? He said something like, my equations explain all of chemistry, the rest is just stamp collecting. A lot of physicists say that. Anyway, okay, it's kind of right. Delta ij, no, he's completely wrong. Delta ij, that's what this beast is. This is equal to 0 if I does not equal j, and 1 if I equals j. So this is just a little side thing. I'll tell you, I equals j. It's used a lot. This is actually the identity matrix. It's actually the identity matrix, right? So the ijth entry of this is delta ij. So that's kind of groovy. There's a way of writing it in a nice little fashion. That's a sad looking thing. That's supposed to be a right delta. Okay. All right, craziness. This is going to be 0 unless I equals j. So one of these sums disappear, and we just end up with right? This is an excursion here. We just end up with the sum, and we can just do, say, I equals 1 to n, and we'll have ci squared, right? I has to equal j. So it's ci squared times lambda j times 1. All right, this is where the positive definite matrix business comes into play. Lambda j, if all of the, lambda I, if all of these guys are greater than 0, this is always greater than 0. So this is another, so it leads to an alternate definition. So this is a better definition of PDMs, is that X transpose A, X for A equals A transpose is greater than 0 for all X in Rn. So this funny little construction, which we'll see has value and worth and should be used in the world. This is a nice way, it's kind of a funny way, but it's a nice way of saying that it's a positive definite matrix. Right, so what does this thing look like? It looks like a row, square, column. And ends up as a number. So as long as that's greater than 0, we have a positive definite matrix for all x. So you have to try all x if you like, but a simple way to say it is to say find all eigenvalues. If they're positive, it works. And even simpler is to find all pivots, which we can do. All right. We're going to use this construction. So we've connected these two things. And that's kind of good. Okay, I said the things. Yeah. Okay, great. So, all right, we're sort of moving across into a different definition. So let's use this new construction. Which way should I do this? Bless us all. Okay, so let's imagine, so let's use these. Let's use this thing for good, for the power of good. Okay, so we're going to play around with this thing. And then whether or not A is a positive definite matrix will matter. Yes? This thing? Yeah, that's multiplied by 1. This was what happens to this, right? So these are unit vectors, and their dot product is 1 when I equals j. So that just became a 1. Yeah. So if you like, it's gone by the power of chalk. Okay. Yes. All right. Let's do this. Okay. This is fun. So. Let's imagine we have this function. So we're going to get to this business over here. And I'm going to change my notes because I want x1 and x2. Let's imagine we have this one, x1 squared. There'll be a 2 here for a reason. x1, x2 plus c x2 squared. So this is a function. So now we're in 3 dimensions. Right? So this is a 3D function. What can these things look like? It's a quadratic equation. It's got x1 squared, x2 squared. What could it look like? Again, we had a banana. I literally have a banana with it crossed out, so that's wrong. Okay? Yeah. I said that. Okay, all right. What could this thing be? Well, it could be, if you've had to sit through maybe, multiple variable calculus. You might know about these things. I feel bad for you. It could be one of these, right? So this would be, a global minimum. Could be like that. It could be a little hillock. A hillock, a very big hillock, of course. Hillock. It could be. Let's draw one of these. Could be a saddle, right? It's true, actually, right? I'm not making this up. This could be something like this. a saddle. Yeah? And that's it. So there's something about the A and the B and the C that are going to give us those things, right? Somehow this has something to do with matrices. So let's make it. Let's use Monk suggestions to make it into matrices. Okay. So the statement is going to be if this had let me do the thing. Yeah. Okay. So let's come back over here. And let's force it into this funny thing that I've started to talk about today, this X transpose A times X. So if we wanted to look like that, it's going to be X1, X2. Let's think about what could be in the middle. I guess I'm drawing the right shape. X1, X2. So column vector, row vector. This is X. Transpose, this is X. This is A. Very exciting. I'm very excited. Can anyone see what the numbers, the letters should be in this matrix? It's going to be a 2 by 2. Anyone want to make wild guesses as to what could go in here to work out? Yes. 50 points to Gryffindor. Correct? Right. Fine if you're in Slytherin. There are no discrimination. Okay. I guessed. Okay. A, B, B, C. Very good. So let's see if that works. We believe. And that's why this was a Monk suggestion, right? The monk comes in through the threshold, crawling, looking for water, and says, "Make sure there's a 2 there." Okay. But in Latin, because they speak in Latin. It's very confusing. And sometimes Esperanto. Crazy. Esperanto. Humans. So silly. Okay. There's a move again to try and make English spelling more simple, because that will raise people's general ability to do things, is the idea, that people will be able to think better. Webster, right? Good old Webster, good American dictionary maker person, apparently went before Congress, I think, and said, let's make it phonetic. Let's just make it totally phonetic. Let's throw everything away. So that's why color ends, you drop the U, but it's still a ridiculous word. I mean, C-O-L-O-R should be K-U-L-L-A, right? George Bernard Shaw, excursions are happening, I'm sorry. Does anyone, you probably know this one. Have you seen that one? What's this? What is this word? It's fish, right? Right, so this is O as in women. That's enough. I mean, it's just to point out and maybe emotion. It's to point out the lunacy of English. But that's a great thing. That's why Monty Python exists and so on, right? It's because English language, this is my hypothesis, is because English is insane, because everyone invaded them for a long time. You had the Danes were in there for a while, and then the French came in and made everyone speak French. So joyously, you have the very nice aspects like all of mates, the meats that you would eat are French words. The animals are English words. Because, only the upper crust in the 1100s or whatever were eating those things. The rest just had a cow. You didn't eat the cow. So veal and pork and all those things are good French words. All right, anyway, but the madness is baked in, which is great. It's really great. It's just baked into language. You can't help but be ridiculous. That's why the English are no good at anything except humor. Anyway, and exporting humans to the rest of the world. Okay, 25% of them came to here, actually, by the way, before that War of Independence. And then they said, well, maybe we'll send them somewhere else. Okay. I know. All right, okay, silliness aside. Okay, so we could have these things. This was a very nice idea. First question you should always ask from now on is, how can I use a matrix in my problem? Even if it's an English essay, okay? I hope that's what we're getting with this class. Okay, let's see if this works. The monk whisperers, okay. Oh, you could be matrix whisperers. I like that. Okay. So let's multiply it out. Let's see what's happening. And there's goodness here. So there's going to be an AB. Let's just do the whole thing. This is AX1. And you kind of see what's going on. BX2, right? Picks this piece up. And then the BX1, that's where we're getting a cross term there. And then CX2. So in a way, what happens is this X2 hits here, and this one hits here as well, right? So you'll end up with this C times X2. Let's do the next one. We're going to have X1 times all of this, and X2 times all of this. So it's AX1 squared plus AB, plus X1 times this, so plus, there's our cross term, one of them. And then here's our second cross term. So let's write it maybe as round the other way. X2, X1, there's a B, and then plus C X2 squared. And then that all gives us what we wanted. So it's 2B, X1, X2, plus C X2 squared. Awesome. And the monks were, right? So this dying monk told us to put a 2 there. And so we have these B's here. We made it a symmetric matrix. You don't have to, right? We could put 2B here and a 0 here. That will work. But then we don't harness the joy and power of symmetric matrices. So, note, foolish monks, right, could choose, these are the ones who didn't make it, could choose the ones who chose poorly, 2B, 0. That would work. But A does not equal A transpose. Can't use superpowers. Right? All right? If there's a menu and there are various matrices on the menu, always choose the symmetric matrix. Okay. So, what we're going to see is those shapes up there, they're going to connect to whether it's positive definite or not. So this will be a positive definite matrix. This, because it's a 2 by 2, will be one where you have a positive eigenvalue and a negative eigenvalue, and this is 2 negative eigenvalues. We don't really talk about negative definite matrices, but that's just a flip of the whole thing. So we're getting that as well. All right. And of course, we're thinking about million by a million matrices, because that's what we do. All right, so let's try this one. Let's try this one. So you can eventually you can just look at this and you say, okay, here's the x2, x1 term. Sorry, here's the x1, x2 term. When I make this matrix, I'm going to have to half whatever that number is. Right, so if this number is 13, you're going to put 7.5 here, wow, 6.5 here and 6.5 here. You're going to divide it. And this, if this was, there was an x cubed term, and then there'd be an x1, x2, x2, x3, x1, x3, you'd do the same thing. You put them across the diagonal. You balance it out. Because we're desperate for symmetric matrices. Okay, let's try another. So let's do a concrete example. So let's try this one, fx1, x2. See if you can do, just write it down. 2x1 squared minus 2x1, x2 plus 2x2 squared. So rewrite it in this form. x1, x2. You would never think matrices are important here, but they are. Which one did I give you? That one, yeah. All right, I mean, we've got the plan here, so it's going to be, scrabble around for some things. So it's going to be 2, 2, minus 1, minus 1. And this is, the other day, from last lecture, horribly, I'm always asking to remember things. This was A1. We had 3 matrices, A1, A2, A3. This was A1. And we found from that one, for this guy, we had lambda 1 equals 3, lambda 2 equals 1. It's a positive definite matrix. And we had pivot 1. I always want to do that. Pivot 1 was 2, and pivot 2 was 3 halves. Pivot 2 was 3 halves. So this is going to tell us, and we're going to get to it, but this will, so we'll see that fxy, am I saying that right? fx1, x2, I don't want to do xy, is a global, has a global minimum. Right? It's one of these guys. Because of this, because the eigenvalues are positive, because the pivots are positive. Let's do, we had another one. Let's get A2. So this is examples. This is another example. So we're going to get to why this is true. This is x1, x2 equals, and this shift was to change the last one. It's 2x1 squared minus 2x1. So many beautiful things. 2x2 squared. Right, so immediately you want to set this up. Right, if there was an x3 here, you'd write x1, x2, x3, x1, x2, x3, etc. Fill in the good guys. So it's the same. We've got a one change. Kind of nuts, actually. Yeah. Okay. So I've written these things down for this one. So, right, what do we get? 2, and then now there's a minus 2 here. Minus 2, minus 1, minus 1. This is, from the other day, this was what we called A2. And just going back to from before, we had lambda 1 equaled root 5. Lambda 2 equals minus root 5. And the first pivot is 2, and the second pivot was minus 5 halves. Yeah. So this is not a PDM, public display of matrices. Not a PDM. And the mixed signs means that this is f x1, x2 is a saddle, complete with stirrups. Okay. That is harder to do in Mathematica. Yes. Yeah, that should be a D. You're right. Okay. Thank you. Graphomania is a problem. Okay. Thank you. So let's see why that is. Okay, so we're going to work on these two examples a little bit. Let's go back to this first one. So let's complete the square for this thing. All right, so let's see why. How this all works. And the thing we're going to work on is completing the square. Remember this business? Complete. We've done this. Yeah? We've got x something times x squared plus something times x plus a number. You complete the square. You have some funny little thing for doing it, which I don't understand. Well, you can do it with this. So let's try first example. So I'll call it A1. So if we have fx1, x2 equals 2x1 squared plus minus 2x1, x2 plus 2x2 squared. Let me just say something. Yes, these are positive numbers, so it grows in that direction, but that negative throws you a little bit. It's not obvious, right, that this would necessarily be a global minimum. It's not completely obvious, I think, maybe. Right, if these were all positive numbers, then yes, everything grows as you move away from 0. Okay, so this thing, let's complete the square. And we're going to do it with respect to x1. So let's try that. So should we complete the square on a simpler thing? Just as a refresher? Just because that's awesome? Okay, you like doing it? All right, let's a little example. a refresher. Okay, I'm making this up. Let's say x squared plus 4x plus 7. What do we do with that? Yeah, so you halve this thing here. Yeah? So we'd halve that, and we'd say x plus 2 all squared, right? Half of this. And we get an x squared plus the 4x. We get a plus 4, but that we want to get rid of, so we get a plus 4 out of this, and we'd have to subtract that off plus our 7. So then this would be equal to x plus 2, this is a nice thing, plus 3. Okay? Seen these things? Yeah? And this is an easier thing to plot, right? You know where the, right? So it's got a minimum x equals minus 2. All right. So let's do it now. We've got x, we're not going to worry about x2 squared, right? We'll just treat as numbers. And we're going to complete the square with respect to x1. All right, so let's try this one. So fx1, x2. There is an extra piece. We've got a 2 here. So we pull the 2 out. Right, if we had a 3 here, we'd have to pull that out. So let's pull that out first, and then work on what's on the inside. Oof. Headache. Okay. Did I hand those solutions around? Okay, right. God. Okay, equals 2. And now it's going to be x. We're going to halve this, right? We've got a minus 1 here. So we're going to half that. x1 minus a half. You can help me when I get, and there's also an x2, you see. So this is minus 1 times x2. That's the factor that's multiplying x1 here. Is that okay? Right, the factor multiplying the x was a 4. Here we've got this blob. We're thinking of x2 as just a constant. It's all about x1. So there will be an x2, and then we square all of that, right? So this is going to give us x1 squared. It's going to give us minus x1, x2. And then we're going to get this extra business. We're going to get a plus a quarter x2 squared. So we'll have to subtract that off. Plus x2 squared. Am I getting this right? What am I doing wrong? Oh, that's all right. Yeah. Okay, so there's all of that. Right? Is this good? Team? Am I lying to you? I don't want to lie to you. All right, let's keep going. We've completed the square. We're going to keep that as a nice little blob there. So the first part is 2. That's going to be x1 minus a half x2 squared. Always magic. And then this piece here is 3/4 of x2 squared. Correcto? And then multiply by 2. Excitingly multiply by 2. Plus 3/2 x2 squared. So now you can see it's a square, something positive times a square plus something positive times a square, which is manifestly positive, right? So and it will grow. So now this is kind of clearly, right? So this is positive, positive, right? A clear minimum. Clear global minimum. Global minimum. Wasn't as obvious what I'm trying to appeal to you, right? There was a minus sign here, it's a little messy. It's not obvious from this. Now it's cleaned up. We've got positive number times a square plus a positive number times a square. Good. So it's definitely like this. So is there anything about those numbers that appeared? Let me write them in different colors. No good reason. Oh, that's terrible. Okay. Purple. Actually, through my undergraduate career, I just record on yellow paper with purple pen. That was very important. I thought it made me better. Just an idiot. Okay, yes? Yes. So, let me make better brackets as we would in a nice journal paper. Although we do use square brackets here. So there was a 2 that got pulled out. Right? So you're right, there's a 3/4 multiplied by 2. Can you read that? Anyway. What about those numbers? Pivots. The pivots are right there. Awesome. And that's pretty, you must be excited by that. So this is pivot 1, pivot 2, and this is, and this whole thing in here, right? So what do we do when if we do a row reduction on this? This is the right one. If we do row reduction to get rid of this guy, it would be R2 prime is row 2 minus something times row 1, and the thing in the here is minus 1 divided by 2. This is L21. So that's what this business is here, in fact. So this whole thing is L21 from L, from the LU decomposition. So all along, we've had this row reduction thing. I know this is thrilling for you. The row reduction thing, we've got the Gaussian elimination business. Turns out to have this connection to completing the square and maybe understanding these shapes here. All right, well, let's keep proceeding with this madness. We're also going to do it for the second one. So that was A1. So A2, let's see if you can do this. So f x1, x2, it's the same thing, but we change that sign there. So it's 2x1 squared minus 2x1 x2 plus, minus 2x2 squared. So everything's going to work out in the same way. We've got to pull that 2 out. We're careful about this. We'll pull out our 2 with x1 minus x1 squared minus x1 x2. And then we complete the square in here. Right, it's always good to get a 1 in front there. So this is 2. Same business. Minus a half times x2 squared. And then that would create a plus. We get a plus a quarter x2 squared here. That's bad, so we have to subtract that off. Minus a quarter x2 squared. And then this is minus x2 squared. All of this is a bit different now, right? So it's minus 5/4 of x2 squared. Algebra is fun, isn't it? Okay. Yes. All right, and if we expand this out, we're going to multiply it through by 2. So we're going to get, let me use the funny colors again, we're going to have a 2. And then we're going to have x1, same thing as in here, minus a half x2 all squared. And then that 2 is going to multiply here again. So it's going to be minus 5/2. Let's make it blue. It's going to be minus 5/2 of x2 squared. And once again, we see these things. Pivot 1. Again, but this is for A2. This is for the matrix A2. This is pivot 2. All of this is pivot 2. And this is L21. Groovy. And we can see that this is a saddle now. We have a squared term here, a squared term here. The minus is here. The positive is here. So this is manifestly a saddle. Right? So the one positive, one negative. Okay, so this is for things in 3D. Yeah, so let me write it down. So completing the square in this elaborate kind of way, right? You keep going on, matches up with Gaussian elimination. Which is #cray cray. Okay. All right. I know, it's old terminology. Sorry. Okay. That's what monks say. Great. So let's use this kind of same thing, but now we'll work with an ellipse. We need to solve this one over here. So if you like, this is what we're not going to use this one. We're going to use a minus sign, I guess. Yeah. Well, we'll see what I'm going to do actually. Equals 1. So that means, essentially, we're going to take one of these things and set it, when does it equal 1? And that's a slice through this thing. It's a little slice of it. And these things look like ellipses when you take a slice through it. So let's draw that out. And this is another fundamental kind of thing that matrices can do for us. Okay, it's called the principal axis theorem. All right, well, I guess I am going to depart from the one that I had before. Okay, all right, fine, crazy person. Let's do a slightly different one. Okay, principal axis theorem. You know what? Let's see. 14b. Okay, before we do that, sorry. Okay, let me just finish this. So we've got the, yes? Positive? That's positive? That's positive? Okay, sorry, yeah. It's possibly I'm the only person in the world who writes that, I'm not sure. Positive? Negative? Okay, yeah. It's a VE, yeah. It's a VE. God knows what I'm doing. I don't know why I'm doing that, but I do this. Sorry. Okay? Anything else? Okay, so is this always true? Does it always work like this? We've got these two examples where the pivots popped out and an L popped out in here as well. So let's see what's going on in general. Right, so sort of a general story for completing the square. And we're going to do it for n by n's. Very nice. And we're going to do it also for eigenvectors as well. Okay, so we've got this. So X transpose A times X with A equals A transpose. So A equals A transpose, what we can let's just ignore the possibility, let's ignore row swaps. We usually do this, it's a bit bad, but let's ignore row swaps and just say A can be written as L D L transpose. We had this the other day. If A is a symmetric matrix, this is what U is. It can be written as D L transpose. So this always pops out. If you take the transpose of this, you get L transpose transpose pops out the front, L transpose goes to the end, and D transpose is D because it's already diagonal. So it's manifestly, this is clearly, it's a dangerous word, this is clearly symmetric. I'm going to say that, right? This is diagonal pivots in here. So we've forced this. We want this to happen. As I said, we didn't have to do this minus 1. They have to add up to minus 2. So it could be 17 and minus 19, but that would be a terrible thing to do. Okay. All right, so we're not going to do that. Yeah, so let's just stick this. Or in Australia, we'd say we're going to bung this one in here. Let's bung it in. So this becomes X transpose, and let's put all the goodness in. So we've got LD, L transpose, times X. Yes. And let's combine these two. So if we combine these two, what do we get? How do we combine them? What's a good way to combine them? It's a sneaky thing to do here. Got a transpose there. We like X. We do a little switcheroo. We can do this. L transpose X transpose. Very sneaky. And then D stays the same. And then this blob is L transpose X. Right? So this blob are the same. D is in the middle. So this is, let's call it Y. This is Y, D, Y transpose dy, where Y equals L transpose times X. So this is the change of coordinates. Right? So this is a change of coordinates. Change of basis. Think of it like that. So that's what we were doing. We were changing to a new basis. So instead of x1 and x2, we're going to have a new, this is going to be our y1, and y2 is going to be the old x2. We changed to a new basis. And in that new basis, it's better. Right? It becomes clearer. Let's see. Yes. Good. All right. I think that's good. Yeah, it's diagonal. These things are the same. It's diagonal. So before we had, it's going to be a11 times x1 squared. Well, this is a big mess. This is a big, horrible mess, right? This is a big mess. It has cross terms in it. This is diagonal. So the new piece here, let me write it here, because this is just diagonal. Can I do that? D1, dot, down to dn, zeros. The next step here is that this equals y1 times d1 times y1. We'll get that. So we'll get d1 times y1 squared plus d2 times y2 squared plus dn times yn squared. So that's exactly what was happening. Here's pivot 1 times the new y1 squared plus pivot 2 times the new y2 squared, and that will go on and on. So if all of your pivots are positive, right, if you have a PDM, then you have a nice minimum structure. That is fantastic, and let's do it another way. We know another fantastic, this is an even more spectacular factorization. Right, so let's note, right, so if all di are greater than or equal to 0, then this thing that we started with, x transpose a, x is greater than or equal to 0. Right? So it's a positive definite matrix. It's all connected. So we could also use this, because we made A into a symmetric matrix. Also use our excellent friend Q, lambda. We could go through these ones. Pivots are of interest because they are easier to compute. This thing is a bit harder to compute for large matrices, but it is magnificent. So if we did that, we would have x transpose A times x. Yeah, I'm going to do all of this. This is great. X transpose, and then we'd stick this in, Q, lambda, Q transpose times x. And we're going to do the same sneakiness. We'll put our Q transpose here with our x. And then we'll have our lambdas in the middle and our Q transpose x. So this would be a new kind of thing. Let's call it, I don't know, Z transpose this character, the eigenvalues Z, just a little z. Let's not get carried away. These are vectors. And we'd end up with lambda 1 times z1 squared plus lambda 2 times z2 squared plus lambda n zn squared. So it's the same story. So there are these different bases we can change to that make the thing clear. And the eigenvector basis is the beautiful one. But again, if all the lambdas are greater than 0, we have a global minimum. If they're all negative, we have a global maximum. We can understand something about it. All right. And I think I want to add, madly I'm going over here. There is even an even stranger business. Should I say that? Sort of a side note. Okay. All right, so this is, factorization. This is just another thing we can do with matrices. Sometimes it's useful. It's related to this, just a bit of a side thing. But let's say we have A equals A transpose, and then we'll have A again. We'll have our L, D, L transpose. So let's do something sneaky. These are pivots. They're yes? Yes. There's a big, this guy's the same. Yep. Thank you. Badness. T. Thank you. Good. All right. Sloppy. So here, these are numbers on a diagonal matrix, and we can actually easily factor that. Right, the square root of a diagonal matrix, we're just going to take the square roots of the entries along the diagonal. Square root of a matrix in general, it's harder, but this is how we get to it. Because from here, we can write this as, have I got this right? Yes. Yep, so we can write this as, let's do, I want to write L, D, to the half, like this. And then this one, we'll move this one around, so it'll be L, D to the half transpose, because the transpose of a diagonal matrix is just a transpose. So that would go over to here and just be itself. This would go to L transpose. So this is of a form, some big matrix Z times Z transpose. It's a useful kind of factorization. Just to say there are more ways to do it, right? We've had lots of things. We've had our eigenvector factorization. We've had LU and LDU. We've had QR factorization. And we're getting to SVD, which is the next thing. Okay. Right, so an example. And we could also do Q, right? So we could also do Q. This one, Q transpose, same kind of idea. It would end up as Q times lambda to the half times Q lambda to the half transpose. And so as an example, let me give you one example that we're working with here. A equals 2, 1, 1, 2. That would be, for this one, if we found its eigenvalues and everything, it would be 1 over root 2 times root 3. Root 3, you don't have to worry about it. We'd have to compute it, but we're not going to do it. Minus 1, and then times 1 over root 2, the same thing, the same blob, root 3, minus 1, 1, transpose. So this is Z, if you like, and this is Z transpose. Okay, yeah, it's good. Okay, there are more things we can do, but that's kind of a good little separate piece. Okay, all right. Okay. Let's go back to playing with what I call the principal axis, what I said we were going to do, principal axis theorem. Right, a lot of the game with matrices is finding a factorization and for whatever you're working on. All right. I know it's exciting. You have to just try to contain yourself. Okay, so let's do principal axis theorem. And we're going to back off from 3D, because 3D is so hard. And we'll just look at something in 2D. So it's going to be just this, 2x1 squared plus 2x1 x2 plus 2y2 squared plus 2x2 squared. That happens so easily. Equals 1. So what this is, something that looks like this. Here's our, let's just say roughly, right? So we've got x1, x2. This will be our function. We're taking a slice. This is 1 here. And so we're taking this part out, and it's going to look like some shape in x1, x2. Right, we're taking a slice through here. So a little chopper. Like a slice through 3D shape, through this surface. Right, and a slice through a surface just gives you this little shape here. All right, so let's figure out what that shape is. Okay. You can mess around with this horrible beast, but we're going to use linear algebra. Of course we use matrices. We use matrices, right? Okay. To understand things. And so this is going to be, again, this is so slightly different from what we had before. It's going to be x1, x2, same idea, 2, 1, 1, 2, x1, x2 equals 1, right? So that's a better way to write this. We've chosen to have an A that equals A transpose. And if you go through and compute all the eigenvalues and eigenvectors, which we're not going to do, 2, 1, 1, 2. So use this where it's Q, it's a symmetric matrix, so it's going to be Q lambda, Q transpose. And if you go through and compute that business, you get 1 over root 2, 1, 1, minus 1, 1. The eigenvalues are 3, 0, 0, 1. And then we get the transpose of this, so 1 over root 2. You must always make them unit vectors. That's why that's what we have. Right. Right, so this is Q lambda Q transpose. Right, so we're going to use this beast to understand this shape. That's what we're doing. All right, we're going to make it. It's good. Terrific. Okay. And that will set us up for SVD. Good. Okay. 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 Good. Yep. All right. Let's do it. The reason we're going to use, right, so we can transform to two bases. For symmetric matrices, if you really want a basis, the best one is going to be the eigenvector one. It's nice, it's orthogonal, it's going to be much clearer. All right. It's going to really tell us what this shape is. And the right angle stuff that's built in becomes manifested. So let's see. So as we said, we have we have this thing, we have this kind of structure times x, and that's going to become x transpose. So as before, let's do it. We're going to have x transpose q lambda q transpose x, and we did the sneaky thing where we said this is really q transpose times x, and this is lambda in the middle with the transpose there. I've got to get that right, and then a q transpose x, and this is going to be y lambda y with a transpose here. So new basis. So let's see what that basis is. So q transpose is times, so y will look like this, q transpose x. So it is 1 over root 2. Q transpose has, let's see, they have 1, 1, minus 1, 1, like this, times x1, x2. So what does that give us? The 1 over root 2 is going to be at the front. 1 over root 2, it's going to be x1 plus x2, and then minus x1 plus x2. And really the new basis is sitting here. Right, this is v1 and v2. Sorry, that's transposed. It's transposed, so let me get that right. Yeah, so the new basis is in Q, which is v1 hat v2 hat, and that is v1 is 1 over root 2 1 1, and v2 hat is 1 over root 2 minus 1 1. Right. So So let's draw that picture. I think we should draw a picture on a separate page. Okay, let me finish a couple of things here. So we've got to this structure here. Okay, so now we have y, a, and there's a transpose here, y, so let's write that out. That's y1, so I'm terribly sorry. That's a lambda. So it's y1, y2, times, in this case, lambda is 3, and then 1, 0, 0. y1, y2. And then let's see how this pops out. So it's y1, it's just going to be 3 times y1 squared, right? It's diagonal, so it's so much simpler. y1 squared plus y2 squared. And all of this has to equal 1, right? That's our equation. So this is what? What's this equation? It's an oval, it's an ellipse, right? Yeah. Yep. Right, so it's clearly now an ellipse, not a hyperbola, right? Ellipse, now clear. And that will always happen if we move to this eigenvector basis. But we have to change to a new axis. So let's do that. Our new axis is our eigen. So it's kind of, this is a funny thing, right? We're drawing ellipses, and somehow ellipses are always built into them. You never had to do this before, but they're always built into them was the eigenvectors of a matrix. Always true. Okay, let's draw it. So our axis was x1, x2. Our new basis is here. 1, 1 in terms of the old basis, 1, 1 with the root 2 here, minus 1, 1. So it is, and we often get this one for these simple guys. This is y1, and this is y2. Terrific. Okay, so this is going to be this is v1. Let me put a little v1. This is 1 over root 2, 1, 1. And if I got this right, it's going this way. That was the plan. v2 hat equals minus 1, 1, with a 1 over root 2. At right angles, right? They're guaranteed to be at right angles because we had a symmetric matrix. Crazy. And in this base, so let's draw this just as if we only had y1 and y2 like this. y1 and y2. Let's just imagine this is our nice basis, right? Where does the ellipse hit on the y1 axis? Here. Am I drawing this ellipse or this ellipse? This one? Should we vote this one? The bottom? It's the skinny one. So when y2 is 0, y1 is plus or minus 1 over root 3. So y2 equals 0, y1 equals plus or minus 1 over root 3. And y1 equals 0, y2 is plus or minus 1. Right, that's all we need for ellipses. 1, 1. What's 1 over root 3? You're going to pull out a calculator, aren't you? It's there you go, 0.577. I used to know those things. Yeah, plus or minus 0.577, something like that. So it's in here, and we draw a nice ellipse. So this is 1 over root 3, minus 1 over root 3. This is minus 1. This is plus 1. So we're fine when we have this simple equation. Let's draw it. Whoop. But now it's rotated, right? That was our story. So let's make this, I guess I've drawn a giant. Let me make these bigger. So I'll make them huge. Sorry about that. It's a bit cheaty. And so that's really 1 there, right? And this will be 1 here, plus 1, 1. And we're rotating it, so the long axis is along y2. So this is going to be a 1 here, and this will be, let's say this is our plus 1 over root 3 on this axis, and minus 1 over root 3. Make it there, minus 1 over root 3 on that axis, and we'll draw a circle. Okay. We've used too many colors, so we can do this. Right, so once we've got the right axis, everything happens a lot, right? Once we've got the right, we've looked at it the right way. To start with, it was, if I raise it, to start with, it's 2x1 squared plus 2x1 x2 plus 2x2 squared is not obvious, right? There's a bit of a mess, some nice symmetry in it. But once you get the right axes, simple, pops out. So, a football. Okay, all right. Okay. What else can I tell you about that? Yep. So that's pretty sweet. So we had a couple of things in here. We have shapes. We have surfaces, right? A lot of the stuff we did was for surfaces, whether they're global minima, global maxima, or saddles of some sort. And of course, if you're in 33 dimensions, you might have 17 positive eigenvalues and maybe 16 negative eigenvalues. So that means it's some complex, ridiculous saddle. 0 eigenvectors means nothing. Eigenvalues means nothing's happening along that line. Okay, so that's what I want to tell you about positive definite matrices. It's a little excursion into some other good things. And we will talk about SVD next Thursday and then the next Tuesday. Monday is office hours. Tuesday, challenge level 3. Thank you.